Hello, everyone. We're the Deep Learners, and this is our final project for Data 2040. Our team consists of Yuchen Hua, Yue Wang, Tianqi Tang, and myself, Kevin Lee. And our project is on action recognition with the Human Motion Database. So what is action recognition? Action recognition is a deep learning task that leverages video data to classify what action a subject is making within a video. And because videos are essentially a sequence of frames, which are in themselves images, this task combines approaches used for image data and time series data. So you'll see the incorporation of convolutional neural networks with recurrent neural networks here. And there are several possible application domains for action recognition, including but not limited to surveillance, human-computer interaction, sports analytics, and wildlife observation. Our data set, as you can see, is HMDB 51, which is actually one of the largest data sets designed strictly for action recognition and a benchmark data set for this task in the literature as well. It consists of approximately 7,000 video clips scraped from movies and YouTube and covers 51 unique actions, each with over 100 clips, and are evenly distributed throughout the data set. And also a fun fact, this data set actually comes from Brown's very own SARE lab, which is headed by Thomas Sayre, who is a professor in the Carney Center for Brain Sciences. So now let's get into the data preprocessing and augmentation. Data preprocessing and augmentation is similar in videos as it is in images, except it has a few additional subtleties. And like I said before, videos are at their core sequences of images. Thus, individual frames, which are images, like I said, are temporally related with one another. So image data generator, which is commonly used for image augmentation, is good for augmenting individual images. But when you're considering a video, it fails to consider the temporal relationships between the images. But luckily, there actually exists a library called the Keras Video Generator that actually deals with this problem itself. And it comes with 3 different generators, and we chose to use one of them, the video frame generator. So in video frame generator, you can specify how many frames you want to extract from the sequence and that you want to augment. And we chose 5 frames. And video frame generator then maps the same augmentation properties as defined in an image data generator, and then applies the same augmentation to all the images within a sequence. This then is able to augment the images while preserving their temporal relationships with one another. And as you can see here, we chose the following properties to capture the diversity of video image qualities, from those in movies to those that you see on YouTube. And we use this generator for all the models that we explore, which we'll talk about next.
I'm Yuchen. I'm going to talk about the several model we have implemented on this action recognition task. So basically, we're using transfer learning combined with the bidirectional Lstm to process our sequential data. The model we have tried include MobileNet, AlexNet, and also DenseNet. What makes the MobileNet different from the normal convolution is that it uses depthwise separable convolutions. Instead of processing the different channels at one time, the depthwise separable convolution process the different channels, use different kernels, and then stack up all the results to get the output image. So it makes the training much faster. Here is the structure of our MobileNet. As we are training on the fewer classes, which is 4, we just unfreeze that last 15 layers. And we implement 3 bidirectional Lstm layers. Basically, we get a pretty good result as 90% accuracy. We have used the number of frames as 5, as we are just training the 4 classes. Here is the learning curve. We can see that there is no overfitting issues. Then we decide to move on to the whole dataset. After trial several models, like several different structures, we decide to go with the 2 bidirectional Lstm for MobileNet. And also we implement the L2 regularization. But from the training result, we can still see that there is overfitting issues. The test result is around 70%, which is not bad since this HMDB dataset is pretty challenging. We analyzed that it may be because each class only have 100 files, which make it hard to validate. So here is two training results we include here. The first one we can see here is overfitting issues. After we change the early stop to a shorter period, it becomes a bit better, but it's still severely overfitting. Our solution towards this issue is to try the ensemble method. So next we have tried AlexNet. As we don't have the Keras applications, we need to implement by hand, but I didn't include the top layers here. And also we have used the 224 instead of 227 for AlexNet. As we can see, the training result, this one is from the fewer classes, and this one we tried on 51 classes. Here is still the overfitting issues. So we will try combine the available models later to overcome this overfitting issue.
Hello everyone, my name is Tianqi Tang. I'll talk about a DenseNet adaptation of our model. DenseNet, or densely connected convolutional networks, consists of a series of dense blocks with convolution and pooling layers in between. Each dense block consists of several layers. Each layer receives feature maps from all its previous layers. To do that, each layer first computes its own output from previous outputs, then concatenated with the previous outputs. Because the latter layer receives output directly from the previous layers, the gradients in the backprop procedures can propagate more easily, and therefore, DenseNet is robust against vanishing or exploding gradient problems. Also, the latter layers contain raw outputs from all its previous layers in a block. The features they have are diverse. Our DenseNet model adopted pre-trained weights from ImageNet, excluding the top layers. The base model is entirely trainable. It is then followed by a global max pooling layer, time-distributed layer, two bi-directional Lstm layers, a dense layer, a dropout layer, and the output layer. Here's the results. The model reaches a validation accuracy of 0.7 after 4.3 hours of training. It suffers from an overfitting problem, like other models we have tried.
And hi, I'm Yue, also a student in the Master Program of Data Science Initiative at Brown University. I'll be talking about everything after their head models, which we called action models, and the name just inherited from the Keras video generator author. So as we can see, we're using a time-distributed layer to use their head model on every frame in the sequence that are fed into our model to extract the information that we're going to feed into our bidirectional LSTM layer. As you can see, our first LSTM layer has 256 units, and as a reminder, an LSTM unit is just this LSTM cell that has a forget gate which controls the flow of the previous hidden state. That is basically to determine how much every previous information should be kept, and because of that, it was once called a keep gate. And an input gate, as you can see, determines how much of the C tilde, which is the current candidate state, so it controls how much of that information should be added to the whole cell state of the sequence. It is designed to overcome the vanishing gradient problem so that the layer built with the LSTM cells can carry information from the beginning of longer sequences to the end, comparing to regular RN units. And then we used a bidirectional wrapper from Keras to build bidirectional LSTM layers. The purpose of a bidirectional RNN is to feed the sequence both forward and backward, so that the layer has information on the sequence in both ways. It is analogous to a speech recognition scenario, where someone hears a sentence, "I'm taking a deep, something class this semester where we learn neural networks. The human will then use information from later of the sentence instead of just information before it, because neural network is implicating the missing word to be deep learning class instead of deep diving class. But I'm sure it will be fun in the future to have a neural network recognizing marine creatures when people are taking deep diving classes. However, if that is the case, bidirectional RN will come short because it needs the entire sequence as an input to output a prediction. So this model won't be able to be applied to a real-time classification scenario, maybe about the network classifying the motion of sharks. But overall, that's our choice of the model. So after building our model with different architectures, we ensembled our models so that they can produce a better prediction as a group effort. We adapted the code from random AI, as mentioned in our blog post, and on the right side you can see the results where the accuracy of a single model can be 0.67, 0.68, but our ensembled model, evaluating on the test set we held from the training process, to be 72% accuracy. As you have seen in the graphs earlier, overfitting is a problem for our model, so we are also using ensembling as a method to reduce the overfitting effect, so that it will have lower generalization errors compared to single models. Alright, Tianqi will now talk about future improvements.
Due to the lack of time, we have some potential improvements in mind that may further boost our model performance. The improvements span from making slight adjustments to our models to adopting completely different models. Including more data can be the low-hanging fruit. In our training, we only use 5 frames per video clip. This is insufficient because the transitions between 2 consecutive frames are too large. We can extract more frames to have smoother transitions. We can also use different frame generators. We have tried sliding frame generator instead of video frame generator. The former one produces too many data for us to train, so we mainly use the latter one. But we wish to use the former one to improve the results given more time. So far, we have only successfully used bidirectional Lstm for sequential learning. We may as well switch to a completely different model. One promising candidate we have utilizes BERT, as proposed by Isad Kalfaglu, AL. Compared to Lstm, BERT has the advantages of better contextual learning, enabling parallel computing, and the model also adopts a slow-fast architecture. Although our Lstm model is bidirectional, meaning that it is able to learn both forwards and backwards, the 2 learning processes have little communications. This might lead to inconsistent predictions. On the other hand, BERT is transformer-based. Transformer is able to learn both ways simultaneously, which may give more consistent results. Also, unlike Lstm, transformer doesn't need to train sequentially, meaning that it can process later tokens in a sequence without having to process the previous tokens first. This lets transformers take the advantage of parallel computing, which Lstm cannot. The model also uses a so-called slow-fast architecture, which includes 2 BERT models. One trains on the fast stream of the video frames, and the other one trains on the slow stream. The slow and the fast stream have better spatial and temporal capabilities, respectively. The outputs of the 2 streams are concatenated, which are then used to predict the results. We think that this model handles both spatial and temporal information of the video very well, and therefore we consider it a strong candidate model for our future endeavors.
Alright, that's our presentation from our group deep learners. If you're interested, please don't be hesitant to check out our blog posts. Thanks for listening.